Welcome to Aviation Meteorology. I am Captain Pankaj Pahil. Over the next 10 minutes, we will systematically decode the physics of atmospheric winds. There is an old aviation adage: a mile of highway will take you exactly 1 mile. A mile of runway will take you anywhere in the world. But in order to command an aircraft across that vast distance, you must first command the atmosphere it flies through. Today, we will deduce the strict mathematical formulas that govern air movement, tracking vector balances from the upper stratosphere straight down to the runway surface. This diagram establishes our foundational vocabulary for wind shifts. A clockwise shift in direction is classified as veering. An anti-clockwise shift is classified as backing. To accurately capture those shifts, the DGCA mandates a strict measurement standard. Surface wind sensors must be positioned exactly 33 feet, or 10 meters, above ground level. This specific elevation is required to clear immediate surface friction and localized turbulence errors. Without these universal baselines, analyzing severe weather variables from the flight deck is an exercise in guesswork, and we do not guess. This chart maps the wind velocity spectrum, categorizing intensity strictly by duration and geographic scale. Notice the contrast between the first two nodes. A gust is highly localized and lasts only seconds. A squall sustains its increased velocity for minutes, covers a wide area, and is heavily associated with cold fronts and mature cumulonimbus clouds. For the DGCA exam, focus precisely on Node 3. A gale is strictly defined as sustained winds exceeding 33 knots, or frequent gusts exceeding 42 knots. Node 4 marks the extreme end of the spectrum. Once velocities exceed 63 knots, the system is classified as a hurricane, typhoon, or cyclone. Memorizing these thresholds is necessary for the exam, but predicting them in flight requires an understanding of the invisible physics engine generating these speeds. This diagram isolates the primary driver of all atmospheric movement, the pressure gradient force, or PGF. It acts as the engine, constantly pulling air from areas of high pressure directly into areas of low pressure. The spacing between these isobar rings dictates the physical strength of the force. Close spacing means a steep pressure gradient, generating high-velocity wind. But the air cannot flow in a straight line. Because the Earth rotates, it creates a deflector known as the Coriolis force. This deflects moving air to the right in the northern hemisphere and to the left in the southern hemisphere. Looking at the Coriolis formula below, notice the variable v for wind speed. This proves a critical rule. The Coriolis effect only acts if the air is already in motion. Faster wind yields a stronger deflection. The formula also relies on the sign of latitude, theta. Because the sign of 0 is 0, the Coriolis force is physically non-existent at the equator and reaches its maximum strength at the poles. High above the friction of the Earth's surface, these two forces pull against each other until they lock into a state of mathematical equilibrium. This schematic illustrates that perfect equilibrium, known as the geostrophic wind. Here, the inward pull of the pressure gradient force perfectly matches the outward pull of the Coriolis force, resulting in air flowing strictly parallel to straight isobars. The DGCA mandates 3 precise conditions for geostrophic flow to exist. The air must be above the friction layer, typically beyond 2,000 feet. The latitude must be greater than 15 degrees, and the isobars must be straight and parallel. We apply this directly in the cockpit using Boyes-Ballot's law. In the northern hemisphere, if you stand with your back to the wind, the low pressure center is always situated to your left. This dual-panel visual reveals a common trap on the exam regarding the geostrophic wind scale. Compare the identical isobar spacing at 60 degrees latitude on the left with 40 degrees latitude on the right. Look at the mathematical proof. Because the sign of latitude sits in the denominator, lowering the latitude physically weakens the Coriolis effect. To maintain equilibrium against a constant pressure gradient, the wind must travel faster. Identical isobar spacing yields faster winds closer to the equator. The geostrophic model is a perfect baseline, but nature rarely produces perfectly straight isobars. When pressure systems curve, we must factor in a third physical dynamic, centrifugal force. This outward pulling energy modifies our straight-line baseline into what is called the gradient wind. Focus on the left panel showing a low pressure center. For cyclonic flow to remain parallel to the isobars, the inward pressure gradient force must be strong enough to pull against the Coriolis force and the outward centrifugal force simultaneously. Because PGF is fighting two outward forces, the resulting gradient wind speed is physically slower than it would be in a straight geostrophic system. Now look at the right panel showing a high-pressure center. Here, the Coriolis force pulls inward to balance both the outward PGF and centrifugal force. To generate enough inward Coriolis force to maintain the curve, the wind must travel faster than geostrophic speed. This dictates a vital rule of thumb for the exam. If you use the standard straight-line geostrophic wind scale on a curved system, it will mathematically overread the wind speed for lows and underread for highs. We have mapped the clean vector balances of the upper atmosphere. Now we bring the aircraft down into the boundary layer. This flowchart isolates the mechanics of the friction layer, spanning from the surface up to 2,000 feet. Down here, trees, buildings, and terrain inherently slow the wind's velocity. Recall the Coriolis formula. Because it is strictly speed-dependent, a slower surface wind instantly results in a weakened Coriolis force. Look at the resulting vector on the right. The pressure gradient force remains constant, but it is no longer balanced by Coriolis. The unopposed PGF physically drags the surface wind across the isobars, angling it inward toward the low. This exact mechanical imbalance creates the DGCA golden rule for the northern hemisphere. Surface winds will always back and decrease in speed compared to the upper geostrophic winds. The exam requires exact parameters. Over land, high friction causes the wind to back by roughly 30 degrees, dropping to 50% of geostrophic speed. Over the sea, lower friction means it backs only 10 degrees, retaining 70. Surface friction completely shatters the macro-level equilibrium, requiring pilots to actively anticipate changing wind vectors throughout descent and approach. Beyond general surface friction, pilots must account for local terrain. Stark temperature differentials and physical funnels create isolated, tactical wind patterns. This cross-section models a daytime sea breeze. Land absorbs solar radiation faster than water, heating the air above it. This air rises, creating a localized low-pressure zone that pulls cooler, dense ocean air inland at roughly 10 knots. This convective loop illustrates the nighttime reversal. Land cools rapidly, forming a high-pressure zone that gently pushes air back over the relatively warmer ocean, creating a slower 5-knot land breeze. These localized shifts present immediate tactical challenges. A runway favoring a headwind approach at noon will require a total directional reversal at dusk. Furthermore, advancing sea breezes can rapidly advect dense crustal fog banks directly over the airfield. This topographical render demonstrates the funnel effect. When wind is forced through a narrow valley or ravine, spatial restriction causes severe Venturi acceleration. The Mistral in France is a prime example, routinely generating gale force winds through physical terrain compression. This dual panel compares mountain slope winds. During the day, solar insolation drives light, upward-flowing Anabatic breezes. At night, rapid terrestrial radiation cools the slopes, driving dense, downward Katabatic winds. Katabatic gravity winds are exceptionally dangerous. Heavy, freezing air slipping off massive ice sheets in Antarctica or Greenland can generate sustained downslope velocities exceeding 100 miles per hour, lasting for days. Physical terrain acts as a primary catalyst, generating and accelerating localized weather through these closed thermodynamic loops. This orographic profile outlines the Föhn effect, one of the most frequently tested thermodynamic systems in aviation meteorology. As moist air is forced up the windward slope, it expands and cools. Once it reaches its dew point, it forms clouds and drops precipitation, cooling at the saturated adiabatic lapse rate of roughly 1.5 degrees Celsius per 1,000 feet. Stripped of its moisture, the air crusts the peak. As it descends the leeward slope, it compresses, and warming at the much faster dry adiabatic lapse rate of 3 degrees Celsius per 1,000 feet. The net result is a distinct aviation hazard, a severe, highly localized downslope wind that's significantly warmer and drier than air on the windward side. This master matrix synthesizes the entire curriculum, isolating the forces responsible for every wind system we have analyzed. Each wind type correlates directly to a specific vector competition. Geostrophic winds perfectly balance PGF and Coriolis. Gradient winds introduce centrifugal force. Surface winds inject friction to cool air across the isobars, while orographic winds rely entirely on thermal density and gravity. Memorizing these keywords lets you pass the exam. Fully understanding the physical vector balances beneath them makes you a master aviator. Class dismissed.